So now we're going to talk about, we talked about conventional. Now we're going to talk about trunking technology. Most of you are familiar with trunking, but we'll go over the basics of what is a trunk system. Going to talk about the basic concept of trunking, and we're going to start to talk about P25. Now, P25 wasn't specifically written for trunking, but it does apply to most of the trunk systems out there today. We're going to understand what are the basics of trunking architecture. We're going to talk about the concept of fleet mapping and briefly talk about some of the data capabilities on a trunk system. So why do we have trunking? Well, let's talk about the way it was before trunking. Back in the 60s, 70s, even today to some extent, you had the Part 90 services were all divided into separate radio services. You may remember the regulations. You had the fire radio service, the police radio service, the emergency medical radio service, the local government radio service, um, the motion picture radio service. Everybody had their own dedicated frequencies, and they were theirs to use, and that's the way they operated. Even though they were adjacent channels in the same band, they were designated to different groups of users. So that's the way it was, and to some extent, in some places, still is. Fire has their frequencies, and police has theirs, and EMS and Public Works, they have their own. Sometimes they would share under local government. The problem is it's not very efficient to do it that way. If you have, for instance, a multi-agency incident and police is very busy and requires more than one channel, their users are going to have to wait, while other channels in the local radio service are sitting idle, not being used. So the purpose of trunking is to consolidate and pool those frequencies together and make them available to all the users. And there's nothing new about trunking. It was first developed in the telephone world over 100 years ago. What's fairly new is applying it to systems. So let's talk about conventional versus trunking. Module 1 was all about conventional. This one's all about trunking. In conventional, we had single channel operation, either simplex or repeater operation, but really only one user at a time could be served. In trunking, you take those repeaters and you pool them together with multiple repeater operation. Trunking is still repeater operation, but it's multiple repeater operation. So now you can serve lots of users at one time. You put all those repeaters under central control and management, and you can operate trunking. Trunking is a access method, and so it can be digital or analog. The original trunking systems were in fact analog trunking systems. But here's what they all have in common, whether they be digital or analog. You have a group of repeaters under the control of a trunking controller, which today is basically a server. You set aside one of the channels to be a control channel, and the control channel's purpose is to send signals back and forth on an uplink and downlink to the users, mostly in the background. The users aren't even aware that it's happening, to assign channels and talk groups and basically manage the system. So in this picture, we have a couple of talk groups. We have talk group 1 is fire, talk group 2 are police, and they're going to share a trunk system. So if the animation works properly, the first thing that happens is somebody from talk group 1 wants to make a talk group call, meaning this fire truck wants to talk to another fire truck. So when he first pushes his push the talk button on his microphone, before he even says a word, a digital signal goes up on the control channel and says, I'm fire talk group 1 and I want to make a talk group call. So that goes in on the control channel. He doesn't even He's not even aware it's happening. He hasn't said anything yet. And that is received on the control channel, received by the controller, and the controller will look at his 5 channels, actually 4 available for voice, and decide which one's available to let him use. And then that's the controller's job to make that decision. In this instance, he says, well, channel 3 is available. I'm going to make that one available to you. And it will then send a message down on the control channel downlink to say, everyone in talk group 1, we're going to channel 3. And without any user intervention at all the users go to channel 3. And they can then start talking. Now, somebody from the police wants the same thing. He's in talk group 2, and he says, okay, I want to make a talk group call. What about me? Same thing. The controller will say, okay, talk group 2, I validate you, and who's available to assign to you? And he says, okay, looks like channel 4 is over here, and it gives it to him. I'll go back to that. So channel 4 is now in use by talk group 2. And when the calls are over with, the channels become available for whoever wants to use them. So it's a very simple concept, and it's kind of like the analogy of if you go to the grocery store and stand in line, you could get in the fast line or the slow line, you don't know. And you'll have to wait your turn if your line is moving slow. If you're at a bank, they typically do it different where you get in a queue and the next available teller will take care of you. And that's the way it's in trucking. And it's a lot more efficient. So a little bit of history on trunking. As I said, trunking is neither analog nor digital, but can exist in both worlds. The original analog trunking used what they call fleets and subfleets, which was a hierarchical structure. It used a 3600 bit per second control channel. Then a second generation came along under a project called APCO 16, which set a series of standards for trunking features. And they started to use talk groups rather than fleets and subfleets, a much more flexible architecture. Later came wide area trunking, where you're able to have multiple sites in wide area operation under a zone controller with a 3600 bit per control channel. And then finally, where we are today, P25 trunking. After P25 came along and set standards for digital, one of their set of standards addressed trunking and addressed the use of an IP-based infrastructure along with a 9600 bit per second control channel. So the systems being built today for P25 are compliant with that standard. So if you hear the term P25, that stands for Project 25, which was an APCO project. Originally, it started back in the 90s to develop a set of digital standards. So the first thing Project 25 had to think about was, all right, digital technology is here to stay. How are we going to create standards that allow multiple users to talk to each other so we don't get all these proprietary systems out there? So they developed what they call the Common Air Interface, which is basically, without regard to infrastructure or any of that other stuff, what are the basic over-the-air characteristics we have to make radios talk to each other? And there are certain things in the digital world that you have to standardize on to talk to each other. The first is, how do you access the system? And they decided on a standard called frequency division multiple access. And what that basically is, one channel would represent one frequency pair. So one channel, one frequency. Okay. There are other methods that came along later. What about the modulation? There were two compatible standards that they came out with, and we'll talk about these when we talk about modulation. One called CQPSK, which stands for Compatible Quadrature Phase Shift Keying, the other being Continuous 4-Level FM, or C4FM. And again, we'll talk more about what those are later on. Then they had to standardize on the vocoder. And the vocoder is the software and firmware in the radio that converts the voice, the analog voice, into ones and zeros. And that's not an easy trick, given that the bandwidths are fairly tight. So the first vocoder software that came out was known as IMBE, Improved Multiband Excitation. Then you have to decide, what bit rate am I going to use for my voice channels? And at the time, and remember we're talking 80s and 90s technology, 9600 bits per second was the standard at that time. The system will also support data at the same rate. And finally, we have to decide, what's the channel spacing going to be? Well, they decided, and partly because of the FCC mandate to go narrowband, that they would standardize on 12.5 kilohertz channel spacing. I won't go into all the details on this slide, but I will say that a control channel has a lot of handshaking and signaling going back and forth, both on the control channel and on the voice channel. We talked already how control channels work in the background to register the unit, affiliate the unit, and assign talk groups and channels. But even within the voice channel itself, there's embedded signaling that goes on. We talked about NAC codes, but there's other embedded signaling right within the voice channel itself, including error correction. So that was great, but after a while, especially in the urban area, there just weren't enough frequencies available to license to serve the number of users that they needed. So more technology came along, and some vendors said, we would like to propose that we use time division multiple access to increase the capacity. And so the APCO project said, okay, let's look at that. It looks good, but we have to be compatible with what's already out there. So they developed a new set of standards that they called Phase 2 that would allow for the use of time division multiple access. In other words, slicing the signal in time to support 2 users in the bandwidth that previously supported only 1. They would have a new type of modulation, and we'll talk a little bit about these when we talk about modulation. Also, since this came along later, there were advances in the technology of vocoder, and at that time, the state-of-the-art vocoder was an improved version of IMBE called AMBE. So what else did they change? Well, they needed to have the backward compatibility, so they kept the control channel at 90 bits per second, but they raised the bit rate on the voice channel to 12 kilobit. The data they kept at 9600, the same as phase 1. Failsoft, which is the ability to operate when the system infrastructure goes down using conventional repeater frequencies, they kept that at 9600. And also talk around, which is the ability to operate without any repeaters at all on the repeater output frequency, kept that at 9600. Kept the channel spacing, again, 12.5 kilohertz. But with TDMA, they now can provide twice as many traffic channels in the same channels. So to understand trunking, you have to understand something else called fleet mapping. Fleet mapping is several processes in organizing a trunk system. The first thing you have to do is organize your talk groups. And a talk group is a group of users who need to regularly talk to each other. For instance, if you were a police department and you were in District 1, you normally talk on a District 1 talk group. So that's your virtual channel. And those have to be created and organized. You also have to associate talk groups with what subscribers will have these talk groups. So police subscribers will have police talk groups and fire subscribers will have fire talk groups, and you have to organize that. Also, your dispatch consoles, what talk groups will they have access to? You also have to assign attributes to your subscribers. If you've ever worked with subscribers lately, you know that there are 1,000 different programmable parameters within portable and mobile radios, and you have to decide what features and functions each of these types of users will get. So it's no simple process. You don't just buy a trunk system off the shelf. It has to be designed and configured. So you decide which features are available to which users and which console users, and what system level features are used as well. Most of the systems you're with on the FCC for public safety users will be 700 and 800 megahertz, or there are a few in the UHF band, but there are other bands out there that do trunking, like on the federal government side and in the military. They do trunking on UHF and VHF. There are some FCC regulated trunk systems on UHF and VHF, but the vast majority are on 700 and 800 megahertz. One of the big things about fleet mapping, setting up a system, is IDs. Everything in a trunk system has an ID. The highest level ID is called a Wide Area Communications ID or a WACN ID. That uniquely describes a wide area system. And then the system itself has a unique system ID. See these 4-digit hexadecimal codes, that is a unique system ID. Unique, no other system, no two systems in the world have the same system ID. And then within the system, you might have RF subsystems. If you have zones within the system, you have unique IDs. For instance, a statewide system will typically have multiple zones, and each zone has its own ID. And then each talk group has an ID, so there are ranges of IDs. So the system designer has to set up all these IDs. And finally, each individual unit itself, these are not serial numbers, not hardware serial numbers, these are soft IDs that are programmed into each ID that lets it be recognized by the system. And user groups have IDs as well. So you can see there's a lot of ID numbers that have to be assigned. So how are these used? Well, there's two processes you probably want to be familiar with when a user gets a trunk system. First of all, when you first turn on the radio, your radio will register on the system. In other words, you turn on, your radio will send a signal on the control channel to the central controller telling it who you are. And then the system will look you up in the database and decide if you are an authorized user. And if you are, and I hope you are, it will allow you to access the system. If you are not known to the system, it will not let you access. So that's registering on the system. The second process is called affiliation. So now that you're known to the system, now you have to tell it what talk group you belong to. So if I'm in Police District 1, that's the talk group I'm affiliated to at the time. In other words, where's my channel selector set on my radio? So when you register, the information that you're telling about yourself is who you are on an individual basis, what radio number you are, talk group you're currently affiliated to, what site you're currently registered to. Just like a cellular system tracks what site it's affiliated to, trunking systems do the same thing. You also tell it what capabilities you have, and it knows in its database what you can do and can't do. So you have to register on the system to transmit or receive on a P25 system. You can't just buy a radio, turn it on, and access the system. You have to be known to the system. So it does that by using databases. There's basically two databases in a trunk system, a dynamic database and a static database. And the dynamic database keeps track of you as you move around. It sees who's active on the system, what sites you're affiliated to, what talk group you're on, who you're talking to, all that kind of stuff, and it maintains that in a dynamic database. There's also a static database of all the users who could be on the system who are registered to the system. They may or may not be active at that time, but it has a database that was programmed in of all the users that belong to that system. So what can a trunk system do? Well, today a trunk system can do a lot of different things. It can support multiple frequency bands. So we talk about a 700 and 800 megahertz system, but trunk systems really aren't defined by their frequency. A single trunk system could support multiple frequency bands at the same time. A system can also support both simulcast and voting, and we talked about what those are. And it's very common, for instance, a county level or a commercial trunk system to employ simulcast and voting for wide area coverage. And the system can also support dispatch consoles, especially for first responders, where you have 911 dispatchers who can also um, operate dispatch consoles to talk to the radios. This is an IP-based infrastructure in P25 systems. So as a result, you also have a very sophisticated network management system that monitors all the hardware in the system and lets you diagnose a problem anywhere. The system also supports data, both integrated voice and data, which is done on the regular voice channels. There are also systems called high performance data that set aside specific channels for high speed data, and some of those channels may have 25 kilohertz bandwidth, where the regular shared voice and data channels are 12.5 kilohertz. So these are authorized on 700 megahertz only. You can have different subsystems within the trunk system. You can have an analog subsystem or a digital subsystem. And your system is not specifically either a phase one or a phase two system, but can handle both at the same time. Because you might have some users that are phase one only capable and some that are phase two capable, and you got to be able to support them both. And your trunk system is also going to support customer enterprise networks. These are IT networks that are not specifically part of the trunk system, but can integrate with the data portion of the trunk system. And some examples of those would be computer-aided dispatch systems or unit location systems, the GPS-based vehicle location systems. Those are third-party applications that will work with the trunk system. You can also interconnect to the public telephone network, and you can also have information security and information assurance on your IP infrastructure. The final slide here talks about a integrated P25 network, where we show all those things we just talked about, how a single P25 trunk system can incorporate multiple frequencies, multiple data modes, multiple access methods, third-party enterprise network, telephone interconnect, and data services, as well as network management. All those can be supported on a single trunk system. So that's the last slide for trunking.